Hello everyone, my name is Muhammad Malik bin Zohari. My metric number is 102713. So we'll be presenting husband HYSYS simulation of the CO2 capture for the best amine solvent. So our group consists of Dayang Nuzulaika bin Awamorni and Fatih Nazwa bin Sardon. Hello, my name is Muhammad Malik bin Zohari. My metric number is 102713. So for the abstracts of our project is the global temperature change, which is brought on by the impact of the ozone depleting substances, is a growing problem in the modern world. Due to anthropogenic carbon dioxide outflows and van gas advancement, carbon dioxide has been found to be a major contributor to a global temperature change. Additionally, businesses contribute to the dangerous condition by releasing the corrosive gases CO2 and H2S into the atmosphere. Reducing these harmful gases is important for controlling such condition, and consuming corrosive gases is generally preferred. Amine gas treatment is a suitable is an effective method for removing CO2 and H2S from gas stream to improve safety and environment quality. One of the applicant solvent used in the chemical absorption and desorption process to recover carbon dioxide from piped gas is amine. So the Aspen HYSYS simulation determines the ideal gas stages for the absorber and stripper segments, the ideal absorbent concentration, and the best conditions for carbon dioxide evacuation for each amine dissolvent. Global warming caused by greenhouse gas emission, particularly CO2, represent one of the most pressing environmental challenges of our time. Rizwan Kamar identified the CO2 as having the real commitment towards a worldwide temperature alteration as it is discovered copiously in climate given anthropogenic carbon dioxide outflows. Industrial sources, including power plants and manufacturing facilities, are major contributions to these harmful emissions that require immediate mitigation strategies. The chemical absorption using amine solvent has emerged as the most mature and economically viable technology for CO2 capture. A power plant fuel gas, which usually has emissions of 300 to 700 grams of CO2 kilowatt per hour, enters the bottom of a pack column, flow upwards, and encounters a CO2 absorbing solvent that is circulate currently. Simulation tools, particularly Aspen HYSYS, plays a crucial role in optimizing CO2 capture system before industrial implementation. These simulations enable researchers to evaluate different amine solvent, the optimized operating condition, and determine the most effective configuration for CO2 removal. This research addresses the critical need to identify the best amine solvent for CO2 capture through comprehensive Aspen HYSYS simulation studies by systematically evaluating different amine solvent and their optimal operating condition. This work contributes to the development of more efficient and cost-effective CO2 capture technologies, supporting global efforts to reduce greenhouse gas emission and combat climate change. Therefore, this study aims to evaluate the effects of varying operating apparatus parameters on system performance and to analyze the generation efficiency and reuse potential of the amine solvent in the stripper. Thank you. So for the problem statement, the release of harmful gases like CO2 and H2S by industries contributes to dangerous condition. Second one is degradation products can be released into the atmospheres, posing health risks, carcinogenics, and creating secondary pollution, requiring costly monitoring and mitigation. The objective of this project is to model a simple CO2 capture process using Aspen HYSYS. The second one is to evaluate the effect of varied parameters. Third one is to analyze the generation and reuse of amine in the stripper.
This slide presents the key result obtained from the Aspen simulation of the amine-based CO2 absorption-desorption system. The simulation showed that the MDA solvent effectively removes CO2 from the inlet gas stream. Based on the material balance calculation between the inlet gas and the treated gas stream, the overall CO2 removal efficiency was approximately 82%, indicating successful absorption performance in the absorber column. The absorber operates with a lean amine inlet temperature of 25 degrees Celsius and gas feed temperature of 65 degrees Celsius, which result in amine outlet temperature of 48.45 degrees Celsius. This temperature increase confirmed that CO2 absorption occurs as exothermic reaction within the absorber. The effect of operating pressure was also significant. The gas entered the absorber at 200 kPa, providing sufficient partial pressure of CO2 to drive mass transfer into the liquid phase. This favorable pressure condition contribute to the observed high CO2 removal efficiency. The amine solvent flow rate play a key role in linking absorption and regeneration. At a solvent flow rate of 179.9 kmol per hour, sufficient active amine was available to absorb CO2, while regeneration in the stripper required a reliability of approximately 8.79 multiplied by 10 power of 6 kJ per hour. This indicates that higher absorption efficiency is achieved at the expenses of increased energy consumption. Overall, the result demonstrates that absorber temperature, pressure, and solvent flow rate strongly influence CO2 removal performance and energy demand. The successful regeneration and cycle of the amine solvent confirm that the stimulated process is feasible for continuous CO2 capture operation. Absorber temperature is very important in CO2 capture because its effect how easily CO2 can dissolve and react with the amine solvent. The absorption of CO2 in amine solution is an exothermic reaction, which means heat is released during the process. Because of this, lower temperatures are more favorable for CO2 absorption as they help form stable CO2 amine compounds. At lower absorber temperature, CO2 solubility in the liquid phase increases, allowing more CO2 to be absorbed. This improves solvent loading and overall absorption efficiency. On the other hand, higher temperature reduces CO2 solubility and weaken the driving force for absorption. High temperature can also cause CO2 to be released too early inside the absorber, reducing removal efficiency. Therefore, the absorber temperature must be carefully controlled to achieve high CO2 removal while avoiding excessive cooling costs. In addition, higher temperature of rich amine increase the energy required in the stripper for the solvent regeneration. Absorber pressure is another key parameter that affects CO2 absorption performance. It's directly influences the partial pressure of CO2 in the gas stream. According to Henry's law, higher CO2 partial pressure increases the solubility in the liquid amine, which improves the driving force for the mass transfer. When the absorber operates at higher pressure, CO2 absorption becomes more effective because more CO2 can be transferred from the gas phase into the liquid solvent. This results in higher solvent loading and better CO2 removal efficiency. However, operating at high pressure requires more energy for gas compression and stronger equipment. Therefore, absorber pressure must be optimized to ensure good CO2 absorption performance while keeping energy consumption and equipment costs reasonable.
In this study, we used Aspen HYSYS to simulate an absorber to stripper system for carbon dioxide capture. The solvent was an aqueous amine blend, and we varied the lean amine flow rate between 1,000 and 4,000 kg per hour at a fixed absorber pressure of 200 kilopascal. The rich amine was regenerated in the stripper and recycled back to the absorber, allowing us to study both absorption and regeneration performance. Key outputs include carbon dioxide removal efficiency, reboiler duty, and condenser duty.
From the simulation, we evaluate the CO2 removal efficiency of the stimulated amine-based capture system, which is our key performance indicator because it directly measures how effective the absorber stripper removes CO2 from the gas stream. Using steady-state data from the Aspen, we calculate the molar flow rate of CO2 entering and leaving the absorber to ensure a correct result without errors caused by pressure or temperature change. The calculation was applied consistently across all sensitive analysis cases, allowing us to compare performance under different operating conditions. For the best case scenario, the CO2 removal efficiency was approximately 82%, indicating that the system is effectively reducing CO2 concentration in the treated gas. This result confirmed that under the selecting operating condition, the absorber stripper configuration performed efficiently, and the data can be used to guide further optimization of operating parameters. The figures show how CO2 removal efficiency changes with absorber temperature based on our Aspen simulation. We can see a clear decreasing trend as the absorber temperature increased, the CO2 removal efficiency dropped. At lower temperature, the absorber worked more efficiently, removing more CO2 from the gas stream, which means less CO2 leave with the treated gas. As the temperature rises, the opposite happened. More CO2 passed through, resulting in a lower overall removal efficiency. This indicates that the absorber temperature is a sensitive operating variable that directly affects the performance of CO2 capture system. Importantly, the change is gradual. There are no sudden drop or system instability, showing the system behaves predictably with temperature changes. These results are consistent with previous study on the amine absorption system, where higher absorption temperature were also shown to reduce CO2 capture efficiency under steady-state condition.
Next, we examine the effect of absorber pressure as shown in Table 6 and Figure 4. Increasing pressure from 100 to 250 kilopascal improved carbon dioxide removal efficiency from 80% to 87%. This is because higher pressure increases the partial pressure of carbon dioxide in the gas phase, which strengthened the driving force for absorption. These findings are consistent with Choi et al. 2009 and Mandel et al. 2001, who reported similar improvement in amine system. Overall, absorber pressure fine-tunes capture efficiency with relatively modest energy implication. We then studied the effect of lean amine flow rate as shown in Table 7 and Figure 5. Increasing flow from 1,000 to 4,000 kg per hour dramatically raised carbon dioxide removal efficiency from 12% to 85%. This occurs because more solvent molecules are available to react with carbon dioxide, preventing early saturation. However, this improvement comes at a cost where reboiler duty increased from 1.4 to 8.7 million kilojoule per hour, and condenser duty also rose. This trade-off is consistent with Morse et al. 2012 and Chi 2007, who highlighted the energy penalty of higher circulation rates. To summarize, absorber pressure enhances capture efficiency by improving mass transfer, while lean amine flow rate has a stronger effect on efficiency but significantly increases energy demand. The key takeaway is that optimization requires balancing high carbon dioxide removal efficiency with acceptable energy consumption. This balance is critical for designing sustainable amine-based carbon dioxide capture system.
To conclude, based on the Aspen HYSYS simulation of CO2 capture using various amine solvent, the study identifies that optimal solvent selection varies by industrial application. For post-combustion capture at low CO2 concentration, DGA was effective, 93.6% capture efficiency. Energy consumption differed between standalone amine system and hybrid setups. In hybrids, MEA had the lowest energy consumption. The comparative studies revealed the optimal amine blend composition varied based on focus, which is economic versus maximal capture efficiency. The finding highlight that resolving conflicting performance ranking reflects suitable optimization for specific CO2 concentrations and design goals, underscoring the effectiveness of amine blends in leveraging their complementary strength across applications.